I am Richard.
I am Oliver. I focus mainly on the first 5 questions, plus the extensions in question 4 and question 10.
And I focus on the final 5 questions and their interactive MATLAB models.
I began with the 2-dimensional random walk and verified its displacement statistical distribution over 5,000 trials. I then extended this to Brownian motion. Elastic collisions generate the irregular red trajectory, whilst conserving momentum. We also plotted a graph of square displacement. Next, I modeled Planck body spectra and Einstein heat capacities. The peaks follow Wien's law, whilst the Einstein heat capacities approach the Dulong-Petit limit at high temperatures. In both runs, we included interactive functions that allows the user to update temperatures. For the photoelectric effect, we've plotted 5 distinct methods with different work functions and calculated threshold frequency, wavelength, slope, and slope error. I extended this with an interactive website where wavelength changes electron energy whilst the intensity changes emission rate, alongside material and retarding voltage controls. On the left panel, the controllable settings are shown. For hydrogen, I calculated allowed Bohr level transitions and plotted photon energy against wavelengths for various energy levels. Selecting a spectral line highlights its energy level transition, and the wavelengths are independently checked using the Rydberg equation. We can see this by changing maximum n. That takes us naturally from quantized energies into wave mechanics.
For electron diffraction, I used de Broglie wavelengths and Bragg diffraction to generate the 2 graphite rings as accelerating voltage changes. I also included 2 sliders that can adjust voltage and brightness. The verification plot is clear, confirming the relationship required by the task. For a particle in a box, I calculated quantized energy levels and probability densities as a quantum number and box width changes. I also computed delta x times delta p, verifying the Heisenberg uncertainty principle for every state. For quantum cryptography, I varied Alice and Bob's detector angles and compared classical and quantum mismatch predictions on a live schematic and probability graph. For Compton scattering, I varied the photon scattering angle and calculated the fractional wavelength shift together with the recoil electron speed and direction. The markers update across all 3 graphs in real time. Finally, I generated hydrogenic orbitals from the Schrödinger equations, with Ni and M controlling both 2-dimensional probability slices and 3-dimensional isosurfaces. Changing the quantum numbers immediately reveals the different nodal structures and orbital geometries.
Across the challenge, we tried to go beyond plotting equations by validating models and making them interactive, and included functions that made the user's experience more convenient.
We have included the links to the websites, or on the description of the video.
Based off Richard's question 10, I extend hydrogenic orbitals using a linear combination of atomic orbitals. For H2+, combining 2 1s orbitals produces bonding and anti-bonding states. I then extended this to 3 centers, showing constructive bonding at nodal molecular orbitals in H3+.